All right, and now for the next strange uh, consequence of the speed of light always being measured to be the speed of light, regardless of your motion relative to the light source or its velocity relative to you. Length contraction, which we've already kind of sort of noticed or led into or kind of saw was going to have to be true. So here we go. Let's watch the rest of this video here.
Every second, thousands of cosmic rays, mostly hydrogen and helium nuclei, strike every square meter of the Earth's upper atmosphere. We don't really know where they come from, but we do know that when cosmic rays crash into air molecules in the atmosphere, they create a shower of other fundamental particles. Pions, kaons, positrons, electrons, neutrons, neutrinos, gamma and X-rays, and muons. We know this because we have particle detectors in labs down on the surface that detect the directions and energies of the particles in these showers, and use them to study the original cosmic rays. But there's something fascinating about the fact that we detect a lot of the muons from cosmic rays down on the surface of the Earth. Because muons, if you make them in a laboratory, only have a 1.5 microsecond half-life before they spontaneously decay into an electron or positron and some neutrinos. And yeah, the Greek symbol mu is used for both muon and for microsecond, which can certainly be a little confusing. But the lifetime of muons is really close to a microsecond, so it's also kind of beautifully appropriate. Anyway, the point is that if you have a bunch of muons, you'll only be left with about 50% after 1.5 microseconds, and 25% after 3 microseconds. And after 10 microseconds, there will only be 0.1% of the muons left. Muons don't live very long, just 2.2 microseconds on average. To put that time into perspective, light travels fast enough that in 1 second it could go around the Earth 7 times, but in 2.2 microseconds, light will only travel 660 meters, or less than half a mile. So even muons traveling at essentially the speed of light wouldn't make it more than a kilometer or two before the vast majority of them decayed, which is far less than the 10 or 20 or 30 kilometers that muons do regularly travel from the upper atmosphere to the ground. So how do muons travel dozens of kilometers through the atmosphere without spontaneously decaying, when in fact they should only be able to travel less than 1 kilometer? Time dilation. Yes, because the muons are traveling close to the speed of light, their time literally passes more slowly. At a speed of 99.5% the speed of light, 2.2 microseconds for them would be about 22 microseconds for us, enough time for the average muon to travel at least 6 kilometers before decaying, instead of half a kilometer. And even higher energy muons going even faster would even more easily reach our detectors on the Earth's surface before they decayed. At 99.995% the speed of light, the average muon would live for 220 microseconds and travel at least 66 kilometers before decaying. So from our perspective, the fact that so many cosmic ray muons reach our detectors on the Earth's surface is direct evidence for special relativity and time dilation. But what about from the muons' perspective, where they do only live on average 2.2 microseconds? Well, for them, the answer to the apparent paradox is also relativistic length contraction. From the muons' perspective, it's the Earth and the atmosphere which are moving, at 99.995% the speed of light, towards the muon, and the lengths of moving objects are literally contracted by a factor dependent on their speed. In this case, 50 kilometers of our atmosphere is, to the muon, literally only half a kilometer, which is thin enough for even a muon with a lifetime of 2.2 microseconds to traverse. Well, actually, from this perspective, the atmosphere and ground move past the muon, but at a speed of 300 meters per microsecond and a distance of only 500 meters, the ground has no problem reaching the muon before the muon decays. This, in my mind, is one of the most awesome experimental verifications of special relativity. The unequivocal time dilation, or length contraction depending on your perspective, for objects moving close to the speed of light. They literally couldn't get here if it weren't for time dilation.
So I let the whole thing run just to give a complete picture of that situation. And so the Earth observer sees the muon coming in, and it's not decaying as quickly because it's moving, right? You'd see it in slow motion. Important to note that if you're the muon or riding along with the muon or whatever, you would see Earth in slow motion. Right? This is what both parties would observe. And then they just mentioned how the muon, knowing it decays too quickly to make it to Earth, how does it make it to Earth? Well, it would have to see that distance as being shorter in order to be able to get there. And then what they didn't mention in the video is the Earth observer would actually observe the muon as being length contracted as well. And you might have noticed that the Earth, the round Earth, I'm just circling with my mouse here so you can picture the round Earth, was just, if it was the same height, right, it was just in the direction of motion of the muon that it was contracted, right? So it's like an oval or a pancake version of the Earth. Yeah, so the muon would see the Earth contracted in the direction of motion, and the Earth would see the muon contracted or squished in the direction of motion as well. Okay, so this a little bit of redundancy here, I think, coming up, but yeah. So there's not enough time for the muons to reach, and yet a bunch of them hit. And so how does that happen? Well, due to time dilation, they survive long enough to get there. This is just the math that we did, right, previously. And then from the muon's point of view, it knows its velocity relative to Earth and the distance to Earth measured at rest relative to the Earth and how long it survives for. And so it shouldn't reach, right? So this information would indicate that the muon would not reach, but of course it does, right? And of course, as usual, if you're looking at something that's weird to do with time or distance or velocity, all of them get affected, right? So if the time has to be different, because you're saying, oh, well, how did I reach? I must have been able to reach. If the time was different, then the distance would have to be different as well to compensate, right? So moving muons, of course, experience the same amount of time from their point of view, and so if the I don't know if I need to say much more there, right? But this part here, so they wouldn't be able to detect their time was slow and so on, because that would be against the first postulate of special relativity. You can't do a test to see if you're really in motion. Really in motion doesn't actually have any actual meaning. Anyway, so yeah, the only way to explain the muon making it all the way there is that the distance they would see that they need to travel would be shorter, and that is length contraction, right? So a visual of this, you've got they're cowboys for some reason, so this one's a space cowboy. So this observer would see the proper length of the atmosphere, because the atmosphere is at rest relative to them. They're at rest relative to the atmosphere. But they would see the relativistic time, right? So this relativistic time that it takes, this longer time that it takes for the muon to decay. And then the space cowboy riding along on the muon would measure the proper time for the muon, so that quick time that it decays in, but would see the atmosphere. It would be moving relative to the atmosphere, or the atmosphere would be moving relative to it, right? You can always say it either way. So it would see the contracted length, all right? So that stuff, this is just that same wording there. And so I want to make sure you recognize just, on top of it being kind of tricky to figure out what the event is and which one's the relativistic and which one's the proper measurement, this makes it even worse, of course, right? Or which observation is the proper and which is the relativistic switches if you're looking at time dilation versus length contraction, right? So again, something to watch for. Summary of this again here for us, just to really make sure you hear it and get it, and repetition, clarity through repetition, hopefully. So from the Earth observer's point of view, they would measure the relativistic time of the life of the muon, but the new thing is that they'd be measuring the proper length for the distance of the atmosphere. And so, of course, the muon doesn't decay as fast, and so it has time to reach the surface, right? So that the muon's moving quickly to the Earth, and so it's surfing in slow motion, and so it has time to get there. From the muon's point of view, they're measuring the proper time, right? And so but they know that's not enough time to get there, right? So they measure the relativistic length that they need to travel, right? So time's passing at a normal rate, and so they're like, how the heck can I make it? Yeah, so they must see that length as being contracted. All right. This is wrong here. Proper time. All right. So length contraction distortion videos is pretty awesome. I wish I had been able to see stuff like this back in the day. So glad when I found it in teaching. Let me get it queued up.
The speed of light is the same for everybody. That's really extraordinary.
So here's how Einstein made sense of this extraordinary puzzle. Knowing that speed is just a measure of the space that something travels over time, Einstein proposed a truly stunning idea: that space and time could work together, constantly adjusting by exactly the right amount, so that no matter how fast you might be moving when you measure the speed of light, it always comes out to be 671 million miles per hour.
To respect that absolute quality about light, time had to cease to be absolute, space had to cease to be absolute, and those two had to become relative in such a way that they slosh between each other.
If space and time being flexible sounds unfamiliar, it's only because we don't move fast enough in everyday life to see it in action. But if this cab could move near the speed of light, the effects would no longer be hidden. For example, if you were on a street corner as I went by close to the speed of light, you see space adjusting so that my cab, it would appear just inches long. And you'd also hear my watch ticking off time very slowly. But from my perspective, inside the cab, my watch would be ticking normally, and space in here would appear as it always does. But when I look outside the cab, I'd see space wildly adjusting, all to keep the speed of light constant. So with Einstein, time and space are no longer rigid and absolute. Instead, they meld together with motion, forming a single entity that came to be called space-time.
So he didn't say it super clearly there, but the observer on the road would see the car going by, shrunk in the direction of motion, right? Contracted, length contracted, and time moving slowly. And then from his point of view, the buildings and the person on the side of the road would be shrunk in that same direction, length contracted in that same direction, and they'd appear to be moving in slow motion, right? So the observations always go both ways, which again seems contradictory, but it is just what is true in the world around us. Kind of weird. Oh yeah, this is the other previous example, right, where we look at muons and so on, right? So that was, I don't know why I left that in there, really. And so this is gives you a taste about the kind of numbers that very accurate measurements would give in everyday life. Okay, so common experience highlights certain ways in which observations by such individuals differ. Trees alongside a highway, for example, appear to be moving from the viewpoint of the driver, but appear stationary to a hitchhiker sitting on a guardrail. Similarly, the dashboard of the automobile does not appear to be moving from the viewpoint of the driver, one hopes, but like the rest of the car, it does appear to be moving from the viewpoint of the hitchhiker. These are such basic intuitive properties of how the world works that we hardly take note of them. Special relativity, however, proclaims that the differences in observations between two such individuals are more subtle and profound. It makes the strange claim that observers in relative motion will have different perceptions of distance and of time. This means, as we shall see, that identical wristwatches worn by two individuals in relative motion will tick at different rates and hence will not agree on the amount of time that elapses between chosen events. Special relativity demonstrates that this statement does not slander the accuracy of the wristwatches involved, rather it is a true statement about time itself. So their metabolic processes, their aging, everything would slow as well along with the watch. Similarly, observers in relative motion carrying identical tape measures will not agree on the lengths of distances measured. Again, this is not due to inaccuracies in the measuring devices or to errors in how they are used. The most accurate measuring devices in the world confirm that space and time, as measured by distances and durations, are not experienced identically by everyone. In the precise way delineated by Einstein, special relativity resolves the conflict between our intuition about motion and the properties of light, but there is a price, right? So our intuition about light, or objects, sorry, having velocities that would add up. So if you're running at a certain speed and you throw a ball, the velocity of the ball and your velocity add up. Light just does not do that. So Einstein resolves that, but there's a price. Individuals who are moving with respect to each other will not agree on their observations of either space or time. Not just like there might be a difference or whatever. It's just there definitely is. There was a question in the homework that was to do with, is it possible for the values to disagree or something like that if they're in relative motion? And the answer is, well, yeah, because there's definitely a difference if they're in relative motion to one another. It has been almost a century since Einstein informed the world of his dramatic discovery, yet most of us still see space and time in absolute terms. Special relativity is not in our bones, we do not feel it. Its implications are not a central part of our intuition. The reason for this is quite simple. The effects of special relativity depend on how fast one moves, and at the speeds of cars and planes and even space shuttles and so on, the effects are super small. Differences in perceptions of space and time between individuals planted on Earth and those traveling in cars or planes do occur. There are differences, but they are so small that they go unnoticed. However, were one to take a trip in a futuristic space vehicle traveling at a substantial fraction of the speed of light, the effects of relativity would become plainly obvious. This, of course, is still in the realm of science fiction. Think of the Doppler effect, right? Because the speed of sound is pretty slow, we notice the Doppler effect. We're used to the sound of a vehicle driving by, blowing its horn, going from a high frequency to a low frequency. It's just everyday life for us. It's not weird, right? If the speed of light was a lot slower, that would be the case as well for the length contraction, the time dilation, and so on, right? Nevertheless, as we shall see, as we shall discuss in later sections, clever experiments allow clear and precise observation of the relative properties of space and time predicted by Einstein's theory. In other words, this is all 100% confirmed. This isn't theory. They call it a theory. People need to learn what scientific theory means, right? So the theory of special relativity or whatever. Theory in science means it's the best model we have of what's going on. It's backed by mountains of evidence. It's what science knows about the world around us. They use the word theory to represent that. To get a sense of the scales involved, imagine that the year is 1970 and big fast cars are in, and they're back in now anyways, right? Slim, having just spent all his savings, I don't know if you know, but there was a time when the big muscle cars and so on, it was like the end of an era, really. Government regulations kicked in, and you couldn't really buy cars with big V8s anymore for quite a while. And I guess now they're able to make them nice enough to the environment or whatever. They're making them again, or I don't know why. I don't exactly know why they're allowed to make them again, but they weren't for a while. Anyways, Slim, having just spent all his savings on a new Trans Am, goes with his brother Jim to the local drag strip to give the car the kind of test drive forbidden by the dealer. After revving up the car, Slim streaks down the mile-long strip at 120 miles per hour, while Jim stands on the sideline and times him. Wanting an independent confirmation, Slim also uses a stopwatch to determine how long it takes his new car to traverse the track. Prior to Einstein's work, no one would have questioned that if both Slim and Jim have properly functioning stopwatches, each will measure the identical elapsed time. But according to special relativity, while Jim will measure an elapsed time of 30 seconds, Slim's stopwatch will record an elapsed time of 29.9999999999952 seconds, a tiny bit less. Of course, this difference is so small that it could be detected only through a measurement whose accuracy is well beyond the capacity of a handheld stopwatch, run by the press of the finger. Olympic quality timing systems, or even the most precisely engineered atomic clocks. It's an extremely small difference. No wonder that our everyday experiences do not reveal the fact that the passage of time depends on our state of motion. There will be a similar disagreement on measurements of length. For example, on another test run, Jim uses a clever trick to measure the length of Slim's new car. He starts his stopwatch just as the front of the car reaches him, and he stops it just as the back of the car passes. Since Jim knows that Slim is speeding along at exactly 120 miles per hour, he's able to figure out the length of the car. by multiplying the speed by the elapsed time on a stopwatch. Plus, you can also see that it's, you visually would see the contraction if it was big enough, right? Again, prior to Einstein, no one would have questioned that the length Jim measures in this indirect way should agree exactly with the length Slim carefully measured when the car sat motionless on the showroom floor. Special relativity proclaims, on the contrary, that if Slim and Jim carry out the precise measurements in this manner, Slim finds the car to be, say, 16 feet long when he's at rest relative to it, and then Jim's measurement will find the car to be 15.99999999974 feet long, a tiny bit less. As with the measurement of time, this is such a minuscule difference that ordinary instruments are just not accurate enough to detect it, and Jim wouldn't really notice it in the drive-by and just looking at it either, right? So small of a difference. Although the differences are extremely small, they show a fatal flaw in the commonly held conception of universal and immutable space and time. As the relative velocity of individuals such as Slim and Jim gets larger, this flaw becomes increasingly apparent. To achieve noticeable differences, the speeds involved must be a sizable fraction of the maximum speed possible, the speed of light, which Maxwell's theory and experimental measurements show to be about American 186 miles per second, or 670 million miles per hour, or 3.0 times 10 to the 8 meters per second. For the rest of the world, it works in scientific units. This is fast enough to circle the Earth more than 7 times in a second. If Slim, for example, were to travel not 120 miles per hour, but at 580 million miles per hour, about 87% of the speed of light, the mathematics of special relativity predicts that Jim would measure the length of the car to be about 8 feet, which is substantially different from Slim's measurements, as well as specifications in the owner's manual, of course, right? The Slim's measurement of it on the showroom floor was 16 feet long, and it's shrunk down to half that size. Similarly, the time to traverse the drag strip, according to Jim, will be about twice as long as the time measured by Slim. Slim's clock would be ticking slowly. Slim would also notice the drag strip shrinking in length, right? So it's all self-consistent if you think of all of the changes that everybody observes. Since such enormous speeds are far beyond anything currently attainable, the effects of time dilation and the Length Contraction, as it's called, or the Length Contraction, so as they are technically called, are extremely small in day-to-day life. If we happen to live in a world in which things typically traveled at speeds close to that of light, these properties of space and time would be so completely intuitive, since we would experience them constantly, that they would deserve no more discussion than the apparent motion of the trees on the side of the road mentioned at the outset of this chapter. Or I would say, we talked about the Doppler effect in the wave and sound unit in grade 11. So be similar to that, right? Be like, oh, this is why that happens. No one would be surprised about it. It'd just be an explanation of what they've always observed. But since we do not live in such a world, these features are unfamiliar. And as we shall see, understanding and accepting them requires that we subject our worldview to a thorough makeover. So the preceding discussion reveals that observers see moving clocks ticking more slowly than their own. That is, time is affected by motion. It is a short step to see that motion has an equally dramatic effect on space. Let's return to Slim and Jim on the drag strip. While in the showroom, as we mentioned, Slim had carefully measured the length of his new car with a tape measure. As Slim is speeding along the drag strip, Jim cannot apply this method to measure the length of the car, so he must proceed in an indirect manner. One such approach we indicated earlier is Jim starting and stopping a stopwatch as it goes by. By multiplying the elapsed time by the speed of the car, Jim can determine the length. Using our newfound appreciation of the subtleties of time, we realize that from Slim's perspective, he is stationary while Jim is moving. So this is, again, the idea of the viewpoint of both observers, right? Hence, Slim sees Jim's clock running slow. As a result, Slim realizes that Jim's indirect measurement of the car's length will yield a shorter result than he measured in the showroom, because velocity times a shorter time. Since Jim's calculation, length equals speed multiplied by elapsed time. Jim measures the elapsed time on a watch that is running slow from Slim's perspective from the car, right? If it runs slow, the elapsed time he finds will be less, and the result of his calculation will be a shorter length. Thus, Jim will perceive the length of Slim's car when it is in motion to be less than the length when measured at rest. This is an example of the general phenomenon that observers perceive a moving object as being shortened along the direction of its motion. For instance, the equations of special relativity show that if an object is moving at about 98% of the speed of light, then a stationary observer will view it as being 80% shorter than if it were at rest. This phenomenon is illustrated in figure 2.4. So 2.4 here, right? So there's the car and there's the length contracted version. So the velocity is to the right, and so it's all contracted in the left-right horizontal direction. The constancy of the speed of light has resulted in a replacement of the traditional view of space and time as rigid and objective structures with a new conception in which they depend intimately on the relative motion between the observer and the observed. So length contraction, just a reminder here of who measures what business, right? So for a ship traveling from Earth to Alpha Centauri, the proper time for the trip is measured by an observer in the ship. But since the ship is moving relative to the distance traveled, the person in the ship observes the relativistic length of the trip, right? So what do we have here? So yeah, the Earth observer, let's go, I just talked about the person in the ship, right? So let's go measured from the ship, right? So the astronaut measures, the person in the ship measures the proper time, right? So it's the clock's in the ship for the ship's trip and so on. But the person is in motion relative to the distance, so it would measure the relativistic length. And then from the Earth observer's point of view, they're going to measure the proper length, the actual, the distance between Earth and Alpha Centauri when you're at rest relative to Earth and Alpha Centauri. So that's the proper length. And they would measure, though, the relativistic time for the trip. Right? The Earth observer would, yeah. All right. So the observer on Earth, right, measures, this one here. It measures the proper length. That's the idea of the switch, right, between observers. And so you'd have, actually this is going to allow us to, I just noticed my title here, this is going to allow us to develop the equation. Yeah, right? So observer on Earth, the time dilation equation is already established, and now we're looking at the speed, distance, time information, right? So we've got the proper length, and we've got the relativistic time. Okay, so we've got that equation so far. And so if we rearranged for time, algebraically we'd have that. I didn't bother showing the steps. I think the algebra should be no problem at this point. So the observer on the ship, though, measures the proper time, right? And measures the relativistic length, okay? The contracted length. So from their point of view, they've got L and T0, right? So we're going to put those in, and this one we're going to solve for length. We're actually looking for the length equation, right? So we've got the relativistic length, the velocity times that proper time. Okay, well, proper time, we know from rearranging the relativistic time dilation equation, right? We know we can get T0 to be that. We just multiply both sides by that root. And so there it is, right? And if you look at VT, right, from the previous work here, the last slide, we had this, VT would be L0, right? This thing here is L0, right? So, or put it in as relativistic length, sorry, proper length over V, and then the V's canceled out, or here just rearrange it, so L0 or VT, VT is L0. Either way works, right? Yeah, so boom, there it is. There's the length contraction equation. Again, we're not talking about tensors, we're not talking about vector space, we're not talking about Lagrange operators, all these weird, wild math processes you'll learn about if you go on in physics or in math, whichever. It's pretty basic algebra and logic results. So yeah, there's your length contraction equation. So remember, there's relative motion. Either the the object's moving relative to the observer or the observer's moving relative to the object. It doesn't matter. It works either way, as we've seen multiple times. And of course, we know that, as I mentioned, only the length and the direction of the motion contracts. So the object would be distorted, right? So a Jeep would look like that. So short wheelbase two-door Jeep would be even shorter. And yeah. So if here's an example of a calculation. We have a rod that's 20 meters long when observed stationary. So a car that's 20, like it's basically like, say, a bus. A bus is 20 meters long, or a train is 20 meters long, whatever, right? And if the relative velocity radially in line with the length of the thing was 0.98 c, determine the length of the rod the observer would measure. So a rod is moving relative to the observer, right? And so that would be the relativistic length, and this would be the proper length, right? So we plug numbers in, and we cancel out the c squareds, and we squared, and we subtract, and we square root, and we get an answer, right? So it would end up around 4 meters, so contracted by a factor of 5, essentially. So you would see this rod or this train or whatever this thing is, right, zipping by you. It would look 5 times shorter than normal, right? And you'd also see it moving in slow motion, and an observer in the train, if it was a train, would see you contracted by a factor of 5 in your time, moving slower, right? So it doesn't matter which is moving. It actually doesn't matter. Oh yeah, it doesn't matter which is really moving, which of course really moving doesn't actually even exist as a concept, right? The rod moving away from or towards the observer moving towards or away from the rod, right? It all would mean the same thing. Okay? So if the rod could measure the observer would also be contracted by a factor of 5 and would also have its time slowed as well. And time slowed. And yeah, so that is length contraction for you. Okay, so practice questions and let me know if you need any help. Till next time, thanks for watching.